us. And for the third talk in this session, I would like to invite Floris Bruynooghe with a presentation titled Iroh P2P Quick Transport and Resumable Verified Transfers. Floris is a software engineer at number O, where he built networking protocols in Rust to support user agency. Previously, he's been an SRE and Python developer. When not creating software, Floris can be found in the mountains, climbing, ski touring, or paragliding.
All right, that seems to work. Hello. So yeah, I'm Floris, and I will be talking about something like, I guess maybe a little bit lower in the stack than many things have been here. I'll be talking about Iroh, which is a network, a library for network communication. Which is, yeah, fairly, nearly everyone needs to communicate over the network. But it's also, it does it in, it tries to make peer-to-peer connections, which kind of helps with user agency, etc. So I'll actually also be talking about two separate things here. So like Iroh itself is like the transport protocol. That is the peer-to-peer, the core peer-to-peer library. The transport protocol is basically like what you want to think of it as the equivalent of like TCP or UDP. So all it does is it gives connectivity between two endpoint devices, or two endpoints like sockets almost, like we call them Iroh endpoints, but it's just like two endpoints and a connection between them. Iroh blobs, on the other hand, is an application protocol that builds on top of that. So for application protocol, like the very common example is like HTTP, that probably everyone knows. And yeah, that you can have like many application protocols on top of the transport protocol. And that's also the idea, like people do build lots of different application protocols on top of this. Iroh blobs is like, kind of as the name implies, like just looks at transferring blobs from one place to another, which is something very common. A lot of people here have talked about this already. So that's not an uncommon problem here. But let's start with Iroh itself. Like Iroh itself is like the core P2P library. And the aim here is to make peer-to-peer connections, so like direct connections between two endpoints. So usually when you have a connection between two devices or something, usually you connect from like a client to a server. The server probably runs in someone else's cloud. Like when you're like viewing a photo of that you took on your phone and you're viewing it on your laptop or something, it's probably gone via a server. The idea of peer-to-peer is that you kind of avoid doing that, and you can make a connection directly from one endpoint device to the other. Like you can connect to your, I don't know, your tablet that's at home in your kitchen from here at the conference or something like that. And really what's the differentiator here is that you can accept incoming connections. Normally, your client device that's like sitting at home usually makes connections, outgoing connections to a server on the internet somewhere. But the ability to accept incoming connections is really kind of what sets what defines a peer-to-peer aspect, I guess. That's not always easy. Like, there are a lot of devices, like when you're at home, you have your local Wi-Fi router that does like network address translation, which is like something to kind of to help you access the internet with multiple devices with IPv4. But even so, it's like a sensible thing to have a firewall there. Even if you have like IPv6, you probably have a firewall that refuses incoming connections. So it's not necessarily an evil thing, but there are many devices basically and firewalls on the internet between between your two endpoints that kind of make this accepting of new connections impossible. So you have to, well, not impossible, I guess, but you have to make trade-offs when you want to design a P2P or build a P2P library. And for Iroh, the trade-offs we kind of want is like we want to always be able to connect, because if you can't establish your connection, then you can't do anything. And if you can't do anything, people will just go back to using centralized services. So always being able to connect is really important. Then, like, time to first byte is like, basically, humans kind of want some sort of interaction within a few hundred milliseconds. So if your application has to sit there waiting around for like 10 seconds before it goes like, hey, here is a connection now, that's also not very helpful. And lastly, it's like the low latency, low round trip times kind of thing. And this is really what pushes you to do hole punching and direct connections. Hole punching is the getting a direct connection to go through all the firewalls between the two devices. Like the fewer hops you have in between, the faster you will be, and the more pleasant the experience will be. So that's really the driver to be really good at the hole punching. What does it look like for users? It's like the equivalent is sort of like that we basically, the Iroh endpoint is like your network socket, and then your socket address is the endpoint ID. And the concept we sort of have is like you dial by endpoint ID, you connect to another endpoint ID. The endpoint ID itself is an ED25519 public key. Well, public-private key pair, but the endpoint ID is the public key pair part. That is obviously, that doesn't give you a network connectivity path. You will still need extra information. We'll get to that in the next slide probably, because you still need to know how to actually reach that endpoint ID. But the sort of the API you get is you dial by this endpoint ID. And you get the transport protocol itself, right? We chose, for various circular reasons really, to give you a QUIC transport protocol. So you get a full QUIC API. QUIC is kind of a very, it's kind of the most modern transport protocol, I guess, around. It was initially developed for HTTP3. And the reason there is that it's like, or one of the main drivers was like that you can have reliable delivery of multiple streams without like head-of-line blocking. What this means is like in HTTP, the example there is you're requesting multiple resources, like you're requesting like an image to load on the web on the web page, as well as a giant pile of JavaScript to be able to render the web page or something. And you get those two at the same time, or you want to retrieve those two at the same time, but the network in between is lossy. And in TCP, if you do this all over the same connection, which is kind of what HTTP2 did, if like you get some packet loss on one of those things, all the others are also kind of blocked. With QUIC, the trick they're doing is they're building this on top of UDP. And if you get some packet loss in one of the streams, you can still keep delivering all the other streams while you are resending the packet loss on the stream that happened. So that's kind of the head-of-line blocking thing. So this multiple streams is kind of a nice thing. The other thing is like I said like various circular reasons, right? I said it's built on top of UDP. Turns out like for various reasons that if you want to do hole punching, UDP is way more reliable than doing hole punching on TCP. So that's kind of why we are driven towards wanting to use something on UDP. QUIC is also extensible. Like one of the widely deployed extensions is datagrams, which means you basically can also treat it like a UDP socket almost. So this allows you to like fairly easily port any application, because you can just use a single reliable stream, or you can use like datagrams. and you can swap out to use QUIC under the hood. But obviously, then you need to build on top of that. You need to have some sort of application protocol. A lot of people make their own, which is great, but we also have a number of existing ones that we make. Blobs is the one that I will be talking about. Gossip is like a gossiping protocol. The Radical talk mentioned gossiping a little bit. And Docs and Willow are sort of, Docs is like an earlier version of Willow, actually. The Willow protocol is like developed by other people. It's a very nice thing. Docs is essentially, you can think of it as a cluster or an offline first key value store kind of thing, where all the nodes can sort of always access all the keys and values, and they synchronize whenever they're online. Willow is the evolution of that, I guess, has more capabilities and authorization and things into it. IRPC is just a tiny protocol that kind of grew out of our blobs implementation. We just have found useful. iMessage is another thing that's like extremely experimental, but it's like my personal side quest. It's kind of modeled on the QUIC. Basically, the problem that it tries to solve is that the QUIC API can be like somewhat subtle to use in its advanced use cases. And iMessage kind of modeled its API on ZeroMQ a little bit and try and basically create a very simple API that is really where you can just send messages and it will basically always do the right thing, is the idea. And obviously, like I mentioned, QUIC was developed for HTTP3. H3 is the protocol that's HTTP3 uses. We built a prototype for this. It works well for server sides. The client side is a little bit clunkier than you're used to, I guess. It's a prototype, to my surprise. Surprisingly few people have kind of picked that up and started pushing that further. But yeah, you can totally just run HTTP on top of this because it's on QUIC. So going a little bit deeper into like the architecture of Iroh is like, so I mentioned already UDP. UDP is what enables hole punching. I'll explain hole punching on the next slide, like in more detail how this works. But I explained also like the trade-offs we made of like we want to always be able to establish a connection. This means basically that we chose to go for, to use a relay server. And the reasons for this are several. Like you almost, because of how hole punching works, you always need a third party somewhere on the internet that can tell you some information about yourself on the internet, and that can also like exchange some information between the two peers that want to start establishing their direct connection. So you will always need a third party, and making that a server that we put on the internet, it makes this much more reliable. Obviously, have we now built another central service? That was all very pointless. It's not that bad. The reason is that it's not a central service. Like we identify the relay servers, so just by URL, and you can run anyone anywhere, and they don't have to know about each other at all. They don't incorporate at all. Like you basically, we had this dial by node ID feature, right? And what we do is like the next point in endpoint discovery is we look up like the relay server you might want to use or that we might need to contact you. We get the URL back, and now we can connect to your relay server, start talking to your endpoint. Then the relay server, as soon as we have actually connected, goes out of the picture and the connection just goes direct. So the relay servers really have no coordination needed. They also know very little. They just see some encrypted traffic going from A to B, and then it disappears. They don't even know why it disappeared. Did you succeed hole punching? Did you just stop talking to each other? They have no idea. Yeah, that's kind of the trade-offs of the relay server that come in. So endpoint discovery is like, yeah, this whole dial by node ID thing you have to resolve an address. So the idea is that, or the classical canonical example for us is sort of you have that your endpoint is connected to a home relay server, and that's where someone else can find you to start communicating with you. But you need to know where that is. You might also want to have like public IP addresses that you have available or something. The way we do this is using endpoint discovery. You can basically plug in separate systems. The default one is we go via DNS. And basically the idea there is that you sign your contact information, so your relay URL. You sign that with your private key, with your node ID, endpoint ID now. It used to be called node ID, apologies. And we have a DNS server that basically will make sure that your signature, you submit to it via the p2p protocol, which is developed by independently by Al-Nazar. It's a very nice protocol that allows basically publishing signed DNS records. And if the signature is correct, then we will make it available on a DNS name. You can, again, run this yourself as well in a separate DNS server, etc. Fine. And DNS is kind of a very nice system for this, right? To use it to look up IP addresses, just the same way already. So it's a very good system for this. You can also publish, like p2p also supports publishing to DHT. This is the BitTorrent mainline DHT, like the only DHT that has survived, several decades of hostile environment and is still around and is still big enough to still work. So it's entirely optional. You don't have to, obviously. As I said, all these discovery things are, you choose the ones you want. And then p2p relay is kind of like the last one that I kind of use. p2p is because you have an HTTP server where you have to submit to, you may as well use it for lookup as well, if you want to deal with that. But you do get HTTPS, of course, which might be better than your DNS setup, depending on trade-offs there again. The last one is interesting though, like MDNS, because MDNS is was mentioned in an earlier talk as well. It's like local network. Like your printer at home is announcing on MDNS in the local network, hey, I'm here, you can print to me. Similarly, if you use this here, we use it to say hey, this is my endpoint ID, you can reach me on my IP address here. But that's just a local network. So this means you can, if you get an announcement like that, you can connect to that without even involving a relay server at all. So if there is a possibility of connecting, you don't even need a relay server, right? So even the relay server is optional, though it is kind of easy to always think in the canonical example of having a relay server. So let's go and look at that, because we need to get on with it. Hole punching itself, basically, this is sort of the canonical example, right? You have two devices, they own sit in their own home network with a firewall router, a Wi-Fi router or something between them and the internet. And then we have this relay server that we need to start the direct connections. We want the direct connection, obviously, but the firewalls don't like this. So the trick we have to do is basically you have to, firewalls do let in related packets, right? So in TCP, the firewall knows kind of what incoming packet relates to which connection. And this is also why TCP is kind of harder to hole punch, because you can make routers can make that direct correlation. So they can tell very easily. In UDP, this correlation is just kind of based on timing. So the trick that you want to do is basically you want to tell the two endpoints, okay, we're going to start hole punching now. And then as you say that, which you use the backup communication channel through relay server for, as you say that, you start sending a packet to each other's addresses at the same time. So they go through your firewall as outgoing packets at the same time. Then they cross over somewhere on the internet. And then when they arrive at the other firewall, the other firewall will go, oh, I just sent the packet to that address. Now I'm receiving something, so that's got to be the response. And it will forward it back to your endpoint device. And that's essentially the basics of hole punching. It's more messy because timing, coordination, all this is kind of difficult, but that's the basic principle. But if you listen carefully to that, you have this problem of what do you send this to? because you don't know what your address is on your router. Like, this is the public address kind of thing. Or the fancy word for this is the reflexive transport address. So you need to learn this as well. And this is essentially the address that you see as the sender, right? So the idea is here that if you send something to the relay server, it will also see, or any server on the internet, it will also see that same sender address. And there's a feature basically that, or a small protocol that basically will respond saying, okay, I received your request. This is the IP address that I saw you use. And that's how you learn about what your public IP address is. Stun is like the old protocol for this. It's very simple UDP based. We moved it to a thing called QUIC address discovery, QUAD. The benefits of QUAD for us is that it's encrypted because it's basically inside a QUIC stream. And it's also reliable because of this. And it's still very lightweight. Like, we still get it essentially in one round trip because of how QUIC is built. QUIC is a really cool protocol, actually, where you can do very cool stuff. It's not quite in one packet, but it's like one round trip still, which is pretty cool. And then lastly, like, because if you, it's like, all right. Yeah, but lastly, it's like easy NAT, hard NAT. I'm running out of time, so I'm not going to go into too much detail, but some NATs are harder than others, and some you actually can just simply not hole punch. And that's why you also need the relay server as a backup, because there is a small percentage that just will not work. Then very, very quickly, unfortunately, continuous transfers. Blake 3 hash is like a really cool thing because you can do verified streaming. Blake 3 is the hash function is kind of built out of internally, has a Merkle tree. And the idea is basically that the Blake 3 hash will like, this is different from like how SHA-1 and SHA-256 that Git uses, right? Blake 3 will hash chunks of 1 kilobyte, I believe, and we'll just hash every chunk. And then we'll have this like CV0, CV1 kind of output hashes. And then it will hash these pairs in like a Merkle tree until you get to your root hash. That's your Blake 3 hash. The cool thing about this is that if you, that essentially this allows you, if you have the right information, this allows you by every 1 kilobyte chunk, by every chunk that you receive, you can know that you received the correct chunk. So you don't have to wait until you've downloaded this whole several terabytes of data before you know that your data that you're receiving is actually correct. This is done, the original implementation of this is from Bao, from Jack O'Connor, which is the author of Blake 3 itself. And the idea really is that you traverse this tree in a way where you always send the next thing that you need to be able to verify. So you request the root hash, right, at the bottom. So that means the first thing you have to send, if you want to send strong 0, is like, you send the left-hand parent. But now how do you know the left-hand parent is right? Well, you have to also send the right-hand parent. Now you can compute this, and you can see, oh, it's still the root hash. I'm good. So then you can keep going down the left hand of the tree. You go to the next level of parent. Same problem there. Now you have an unverified bit of data, so you get the parent to the right of that. Again, you can verify the hash of an intermediate parent. Now you can go to the leaf ones in here, and you get the two leaf ones. Same problem again. You get one leaf hash. You don't know if it's correct, so you get the second leaf hash. You can check the parents, and now finally you can start getting chunk 1, chunk 0, and chunk 1. And then you basically go back up the tree and back down the next branch until you get to chunk 2. And you basically build this, you can build this thing for however large your file is, and traverse this tree, and it's always like fully deterministic. And that's kind of how Blake 3 does like verified streaming. I'm probably, yes, out of time indeed, apologies. So there's like a lot more you can do about this. We can do range requests. We also have a thing where you have hash sequences to like transfer collections, etc. But yeah, apologies for running out of time.